I'm Haodong from the Robotics and Autonomous Driving Laboratory, Baidu Research, China. I'm glad to present our paper, Real-Time Volume Estimation of Mass in Excavation Bucket with LiDAR data. In the autonomous excavation task, the real-time estimation of the bucket filling rate and the volume of the excavated mass are essential feedbacks to measure the excavation quality. Previous methods, such as payload estimation, mainly utilize the measurements of hydraulic cylinder pressures and dynamic modeling for volume estimation by estimating the payload carried in a hydraulic excavator. However, these approaches usually require additional hardware sensors, such as sensor calibration, which limits the applications. In this study, to relieve the problem, we utilize visual strategies to directly measure the excavation quality, considering the current autonomous excavators are commonly equipped with cabin-mounted LiDAR and inclination sensors. We introduced an online method to calculate the volume of the mass in the excavator bucket during digging process. This paper presents the following contributions: a dynamic bucket point cloud fusion method, a heat map interpolation method, and estimate the volume from the heat map on the uneven LiDAR data. And an integrated in-bucket mass volume estimation system without any additional sensor on the autonomous excavator. This figure shows our volume estimation pipeline, including a dynamic bucket obtaining model and model pre-saving, post-initialization, registration, heat map generation, interpolation, and the volume calculation model. As the goal here is to dynamically calculate the volume of the mass in a moving excavator bucket. We are looking to get a dense and up-to-date bucket point cloud as well as the latest bucket pose in the LiDAR coordinate system, with the aim of providing a bucket point cloud as complete as possible. We intend to fuse multiple frames of bucket points to get a dense bucket point cloud. To this end, we initially acquire the bucket pose from Rose's transformation tree corresponding with the current frame of point cloud. We then segment the point cloud by the radius search to extract the bucket point cloud. And after about 10 frames of the bucket point cloud are obtained, we fuse them by transforming them through the original pose. Furthermore, it's necessary to initialize the empty bucket model to parallel to the axis for the convenience of bucket part removing and heat map generation. We initialize the model with the PCA results and fine-tune it by hand. This figure shows the dynamic bucket obtaining results. The green is the single frame of the background point cloud, and the right is the segmented bucket point cloud of 10 frames where the bucket is moving, and the blue is the fused and initialized bucket point cloud of multiple frames. We first scan and save the empty bucket point cloud as a model offline and obtain the bucket with mass point cloud online. Then transform the bucket with mass point cloud to the model with T init, where T init is the initial transformation and TP is the transformation from the original pose to the initialized pose. TL is the latest bucket pose obtained from TF. And it's necessary to align them with ICP to improve the accuracy. Thus, we got the final transformation from the SAM to the model as T final, and TICP is the improved transformation from the ICP result. T init is the initial transformation. After the preparations before, we are ready to generate the height map. In our implementation, we generate the height map using the height of points on the z-axis directly, translated by the post initialization step. Those values are stored in a plotted grid based on the minimum and maximum points on the x-axis and y-axis. In the figure shows on the right, A is the empty bucket image, and B is the initialized empty bucket point cloud. C is the generated height map. As we can observe, there are lots of holes in the generated height map, marked as white in D. And those holes must be filled by the interpolation method, where each hole means an invalid value in the volume estimation model. To interpolate these holes, the first step is the interpolation area selection. We firstly check the boundary points on every row and every column, which are shown in the left figure marked as red points. Then the interpolating points are determined by judging whether it's within the boundary points and whether there are the points in its adjacent region. We change the size of the adjacent region to fit the density variation. The interpolating points are marked as blue points in the left figure, and the selected interpolation area of the model height map is shown in the left figure D. As the interpolating points are determined, we interpolate them with the mean height of the weighted points in their adjacent region. The interpolated model height map is shown in the right figure E. And the volume estimation model is based on the interpolated height map, both on the empty bucket model and the real-time obtained bucket with mass point cloud. In the top figure, A is the bucket with mass image, and B the mass point cloud marked as red, and the empty bucket point cloud marked as green. And C is the generated height map of the mass. And D is the interpolation area marked as white. And E is the interpolated height map of the mass. We compute the difference between the height maps on every pixel, where the values are valid on them at the same time. Considering the size of the plotted grids, the volume of the in-bucket mass can be simply calculated as the following equation, where V is the calculated volume, P valid is the valid pixels, L grid is the length of the grid, D is the difference between the valid pixels. To show the applicability and the repeatability of the presented system, we interpolated the different modules in rows and integrated them on the autonomous caption system, which is equipped with a cabin-mounted LiDAR and a 10th generation Intel-Core i7 CPU. To perform the volume estimation of the mass in the Excavator bucket, which is tested randomly in the field. The left figure shows 5 times experiments. As there is not a convenient way to get the ground truth, we firstly generated a height map of the full bucket, which is shown in the right figure, and calculated the full bucket volume. Then we compute the filling rate of the bucket comparing with the directly observed filling rate to measure the accuracy of our approach. The table illustrates the 5 times the experiment results. As it can be observed, our approach gets the expected result on volume estimation. In experiment 1, the estimated filling rate of the empty bucket is 0.93%, caused by the alignment error and the noises. In experiment 5, there is a not scanned area, resulting in a lower volume estimation result. The left table shows the mean parameters of our volume estimation pipeline and the computational times of the individual steps in the volume estimation pipeline are reported in the right table. As it can be observed, the complete volume estimation routine is executed in approximately half a second in our experiments, which makes our approach suitable for online operation. In conclusion, this article introduces an integrated in-bucket mass volume estimation system for the autonomous excavation quality measurement with a robotic excavator. The core of the volume estimation pipeline constitutes of a height map generation and the interpolation module, which is based on the dynamic bucket points obtaining and transformation refinement. And the experiment results shows the applicability and the reliability of the presented system. The limitation of the current system is that the model-based volume estimation process always ignores the points outside the model on the height map. It means that the volume will not be calculated when objects are extended out of the bucket side, such as the stones. As LiDAR collects the data, another limitation is that the dynamically obtained bucket point load will be full of noise, which are the flat-out points when the bucket is moving fast, especially when moving away from the LiDAR. The existence of noise leads to the reduction of the accuracy, especially when SP is employed. Thus, a future research direction of our approach is the noise suppression. Thanks for your attention.
Thank you. So any questions